This is Unit 10, Lesson 5, Inverse Matrices and Systems of Equations. Our lesson essential question is, how can matrix inverses be used to simplify the process of solving a system of linear equations? At the end of this lesson, you'll be able to use matrices to represent and solve systems of equations. Example 1, solve a matrix equation. How can you solve the matrix equation 2, -1, 0, 2 times the matrix xy equals the matrix 2, 8? Let A represent the matrix 2, -1, 0, 2, and let the inverse of matrix A represent the inverse of the matrix. The goal is to isolate the variable matrix to determine the values of x and y. So A times x equals B. I can multiply both sides by the inverse of matrix A, making sure that I do that first. The inverse of A times matrix A times X equals the inverse of A times B. The inverse of matrix A times matrix A is going to give you the identity matrix, 1, 0, 0, 1 in this case, times my variables X, Y, and my inverse matrix times B gives me 3, 4. So X equals the inverse of A times B. So the solution to the equation is matrix XY equals matrix 3, 4. You can check your work by multiplying A by the solution matrix to be sure the product is B. All right, let's try it. Solve the matrix equation A times X equals B for A equals the matrix -1, 4, -2, 2, -1, 0, -1, -4, 2, and B equals 6, 8, 2. So the first thing I want to do is figure out what the inverse of this matrix is. Now it is a 3 by 3 matrix, so we're going to go ahead and use Desmos, the matrix, so we can find out what our matrix is. So we're going to create a new matrix, change rows to 3, columns to 3, and then go ahead and enter. So -1, 4, -2, 2, -1, 0, -1, -4, 2. Enter. Then we're going to do A inverse. Here's our inverse. We're also going to create a new matrix, B, and that's going to be a 3 by 1 matrix, which is 6, 8, 2. Okay, so I'm going to take the inverse of A times B. So A inverse times B. And that gives me -4, -16, -33, which is our answer. So we did our A inverse, which is here. We multiplied it by our matrix B, which we created. So A inverse times B gives me -4, -16, -33. So X would be -4, Y would be -16, and Z would be -33. Example 2, write a system of linear equations as a matrix equation. How can the system of linear equations be represented as a matrix equation? 3x minus 5y equals 7, 2x plus y equals 4. The coefficient matrix has rows which contains the coefficients from a single equation. Each column contains all coefficients of a single variable. The coefficients of y in the second equation is 1. The variable matrix has one column that represents variables in the systems of equations. The variable matrix is sometimes called the variable vector. Use the constant values from the right-hand side of the equations to make the constant matrix. So here my constants 3, -5, 2, and 1 become my first equation. X, Y, because those are my variables, become my second matrix. And my solution, 7, 4, become my third, my constants. How can the system of linear equations be represented as a matrix equation? So I have 3 this time. X minus 2y plus 4z equals 9. 2x minus 8z equals -24. 3x plus y minus 2z equals -1. So very similarly to the first equation, now we just have three variables. Notice, however, that this middle equation right here, 2x minus 8z, we don't have a y. So you're just going to substitute in 0 for that because 0 times y would give you 0 anyway. Remember that any variable that you have without a constant in front of it or a coefficient in front of it is going to give you 1. So my matrix becomes 1, negative 2, 4, 2, 0, negative 8, 3, 1, negative 2. So again, I have all my x's, then my y's, then my z's. Okay, my matrix, normally your x matrix, would be x, y, z, and that equals 9, negative 24, negative 1. You can, of course, solve this using the inverse. So you find the inverse of your first equation here, and you multiply it by your constant matrix. All right, let's try it. Express each system of linear equations as a matrix equation. So the first one I have is 10x minus 9y equals 1, 7x plus 6y equals 13. Okay, so when I go ahead and do this, I'm going to create my matrix. So I have 10, negative 9, so here's my x and my y. In the second row, I have 7 and 6. Then I have x, y, and that's going to equal 113. For my second one, 4x plus 2y minus z equals 14. 2x minus 3y plus 5z equals 20. 3x minus 6y equals 8. Notice that there's no z in the third equation that they gave us, so we're going to use 0 in place of z in this case. So I have 4, 2, negative 1, 2, negative 3, and I have 3, negative 6, and 0. That's my first equation. That gets multiplied by x, y, z, and it equals 14, 28. Example 3, solve a system of linear equations using an inverse matrix. How can you use a matrix inverses to solve a system of linear equations? If possible, use inverse matrices to solve negative 3x plus z equals negative 9, negative x plus 2z equals 2, and 2x minus y equals 10. So notice that I have three variables, so I'm going to have a 3 by 3 matrix for my first one, a 3 by 1 matrix, and then a 3 by 1 matrix. Express the system of linear equations as a matrix equation. So negative 3x plus z becomes negative 3, 0, 1. Negative 2x plus 2z becomes negative 1, 0, 2. And 2x minus y becomes 2, negative 1, 0. I have x, y, z, and that equals negative 9, 2, 10. I find the inverse of the 3 by 3 coefficient matrix using technology. So the inverse of my matrix is negative 0.4, 0.20, negative 0.8, 0.4, negative 1, negative 0.2, 0.6, 0. If this doesn't exist, then your system is not solvable. Step 3, multiply each side of the matrix equation by the inverse matrix. Remember to do the inverse, then your matrix, inverse, then your matrix. Multiplying a matrix by its inverse results in an identity matrix. Multiplying the inverse matrix by the constant matrix gives the solution matrix. Step 4, multiply by the identity matrix and write your solution. The solution to the original system of equations is 4, negative 2, 3. B, if possible, use inverse matrices to solve 1/4 x minus 5/8 y equals 1/2, negative 2x plus 5y equals negative 4. There are two variables, so we'll have a 2 by 2 matrix. Express the system of linear equations as a matrix equation, Cx equals D. C times x equals D. To use the method from part A, you need an inverse matrix. Find the determinant of the coefficient matrix C to see if it has an inverse. We can see that the determinant is 0. Since the determinant is 0, this matrix does not have an inverse. The determinant of the coefficient matrix is 0, so this matrix does not have an inverse. You will have to solve this system using a different method, such as subtraction, elimination, or matrix row reduction. Using elimination results in the equation 0 equals 0, so the system of linear equations has infinitely many solutions. All right, let's try it. Solve the following systems of linear equations using inverse matrices, if possible. So I'm going to go ahead over to Desmos. I'm going to create a new matrix. So this is 3, 4, 3 halves, 2. Okay, and then matrix, 2 rows, 1 column is 8. Okay, so I'm going to multiply C inverse of C times D. I get this little error sign, which means that there is no inverse for C. So I would need to solve it a different way. So if I do 3x plus 4y equals 8, and I have 3 halves x plus 2y equals 5. I'm actually going to multiply this first one, this second equation, by 2 just to get rid of the fraction. So when I do that, I get 3x 2 times 3 halves x plus 2y equals 5, which is going to give me 3x plus 4y equals 10. Okay. So now I can subtract 3x plus 4y equals 8 minus 3x minus 4y equals negative 10. When I do that, I get 0 equals negative 2. That's not possible, so there is no solution. Right? For B, I have x plus 2y minus 4z equals 4, x minus 2y plus 2z equals negative 10, negative x minus y plus z equals 4. So again, I'm going to go ahead and create a matrix in Desmos. So matrix, it is a 3 by 3. So that gives me 1, 2, negative 4, 1, negative 2, 2, negative 1, negative 1, 1. Okay. And then I need another matrix, which is a 3 by 1. And that's 4, negative 10, 4. Oops. So I'm going to find the inverse, in this case, of matrix E, which it does have one, due to the fraction, times matrix F. So I get negative 6, negative 1, negative 3. So that means x equals negative 6, y equals negative 1, z equals negative 3. You could also write it as in parentheses. Either would be correct. Example 4, solve a real-world system of equations with an inverse. The company makes men's and women's sneakers. Last week, the company spent $340 on labor and $420 on materials. How many sneakers of each type did the company produce? Okay, so they're charging women's sneakers, they're charging $10 for labor and $12 in materials. Men's sneakers is $14 for labor and $18 for materials. So formulate. To find a solution using a matrix inverse, first define the variables, then write a system of equations to model the situation. Finally, express the system as a matrix equation. So in this case, they said W equals the number of pairs of women's sneakers produced. M equals the number of pairs of men's sneakers produced. So 10W plus 14M equals 340. So that deals with the labor. 12W plus 18M equals 420, which deals with the materials. I can then set up a matrix 10, 14, 12, 18 times WM equals 340, 420. The first equation represents the labor cost, and the second equation represents the material cost. Now I compute. I solve the system of equations by multiplying by an inverse matrix. I use technology to find that the inverse of 10, 14, 12, 18 is 3 halves, -7, 6, -1, and 5, 6. I multiply each side of the matrix equation by the inverse matrix. Make sure that you put the inverse matrix and then multiply it by the matrix. Remember that multiplication is not commutative with matrices. When I do that, I get the identity times WM equals 3 halves times 340 plus -7, 6 times 420, -1 times 340 plus 5, 6 times 420. When I simplify this, I get W equals 20, M equals 10. The solution is 20, 10, so the company makes 20 pairs of women's sneakers and 10 pairs of men's sneakers. All right, let's try it. For a 3-week period, the same company budgets $860 for labor and $1,080 for materials. How many pairs of men's and women's sneakers can they make in 3 weeks? Notice that the labor and the materials have not changed. So I can go ahead and set up my matrix in a very similar way. So the first thing I'm going to do is write my equations. So I have 10W plus 14M equals 860. That's the cost of labor for the week. My second equation is 12W, cost of materials for women's sneakers, plus 18M, the cost of material for men's sneakers, equals 1,080. I can then change these into matrices. So I get 10, 14, 12, 18 equals, or times, WM equals 860, 1080. And I need to find the inverse matrix of the 10, 14, 12, 18, which we did in the previous problem, and multiply it by both sides of my equation. So when I do that, G inverse times, I get 30 and 40. So I get 30 women's shoes and 40 men's shoes. Concept summary: solving systems of linear equations with matrices. Express the linear system of equations as a matrix equation. So remember that the coefficient in front of the variables becomes one matrix, the variables become the second matrix, and equals the constant matrix. For a 2x2 matrix, find the determinant of the coefficient matrix A. If determinant A does not equal 0, I solve the matrix equation using the inverse of the coefficient matrix. If the determinant A equals 0, I solve the original system with an alternative method. I can use substitution, elimination, or matrix row reduction. For an m by n matrix where n is greater than or equal to 3, use technology to find the inverse of the matrix. Then multiply each side of the equation by the inverse matrix to find the solution. Matrix equations: AX equals B. I multiply both sides by the inverse of A in order to find the solution. And that is the end of Unit 10, Lesson 5.